Induction proofs today and some maybe on Tuesday. And then we're gonna talk a little bit more about how induction goes in the context of binary search trees, which is honors problem 4. It's due next Friday, right? Then something beyond honors material, how to think about a harmonic series. So let's start with those. In my notes here, I have 15 proofs. I don't know if we can get 15 proofs in one day. Maybe we need some for Tuesday. Let's see. Maybe we can. The basic induction proofs, the simplest ones. So again, what is induction? Recap. There is a P of n statement for n. I'm going to put this as an example. Our first proof today would be an example that says if Sn, let's not call it Sn, let's call it sum. Sum of n here is from k equal 1 to n, 2k minus 1 squared. And the P of n in here is to prove, this is a logical statement. Is to say this sum is n times 4n squared minus 1 divided by 2. So that's what I want to prove. And that's essentially what I'm saying is for any n starting at, I guess, 1, this is so the way to think about induction, I have all these statements. And I have an induction step. From now on, we're going to specify which kind is it. Weak, strong, or structural. This is the weak one. The weak one, it's saying if it's true for n, it's true for the next one. Those are the examples we've done last time. From today, I go to tomorrow. From this person, I go to the next person. From this course, I go to the next course, so on and so forth. From n to n plus 1. That is the weak induction. That's what's going to happen here, right? So remember, we have to write the induction step before we prove it. And that's always an implication. It's from here, I get to here. So I'm going to say, well, if my induction step here is if this is true for n, so if k equal n to 1, 2k minus 1 squared is, let's say, n by 3, 4n squared minus 1, then this property is true for n plus 1. So how do I write this for n plus 1? Sum from k equal 1 to n plus 1 of 2k minus 1 squared. So those are the same terms, but it goes further one term. Instead of stopping at n, it stops at n plus 1. Now I have to figure out what this means for n plus 1, right? That would be n plus 1 by 3 times what? 4 times n plus 1 squared minus 1. So what's written here, it's effectively Pn implies Pn plus 1. If this property is true for n, then it's true for n plus 1. Right? Hands up who's with me. The idea of proving this is that if I prove it for any n, this is for any n starting at 1. Then I effectively proved, so let's do here a plan for weak induction. This is not part of that problem. It's a side comment. What I'm trying to prove by induction step is that P1 implies P2, implies P3, implies P of 100, which implies P of 101, and so on and so forth. It never stops, all the way to infinity. because I proved this is an induction step, but then this is another induction step. The next one is P of 4, right? This is another induction step. All those proofs are embedded in here for different ends. For n equal 1, I get from P1 to P2. For 2, I get from 2 to 3. From 3, I get to 3 to 4, so on and so forth. So by proving this, I'm proving the whole chain of implications. If this is true, then that's true, then that's true, then that's true, so on and so forth. Now the induction step doesn't actually prove anything is true. It just proves the implications. To get it done, we need the base case. We'll get to that in a second. But for now, let's focus on the induction step. Remember, you have to write the induction step first. This is not a proof. It's just saying from here, I get to here. It'll be nice to specify for TAs when it's weak, when it's strong. Sometimes they look for those things. But that's not necessary. So now, for the actual proof of the induction step, I'm proving that. It's always good to start with a new customer and ask yourself how the new customer relates to the old customer. That's how you start induction proof. You say, what do I have to do here? I have to deal with this sum, right? So that sum from k equal 1 to n plus 1 of 2k minus 1 squared, who is this related, how it relates to the previous sum, which I already know. This is induction hypothesis, and this is the induction conclusion. So how does this sum relates to this sum? That's the problems we did last time. They all have this like a sum flavor, and what's the relationship exact between this sum and that sum? Yes.
The previous sum of one more term.
Right, is the previous sum plus an additional thing. So we'd write it that way, it's the previous sum, k equal 1 to n of 2k minus 1 squared, plus what's the additional thing? Is the last term on that sum, which is?
2 times n plus 1 minus 1 all squared.
Like that?
Yeah.
So if you look at this sum, the last term is k equal n plus 1. If I put k equal n plus 1, I get 2n plus 1 minus 1 squared. Now if you look at the previous sum, that's the same as this. This is where I applied the induction hypothesis. I say, by induction hypothesis, I already know that this is that. This previous sum, I'm assuming I know Pn is true. That means the previous sum is this thing here. So this becomes, if I plug it in, what do I get? N by 3, 4n squared minus 1. That simply I replace this sum with the value I know. Plus, what do I get here? 2n plus 2 minus 1, that is 2n plus 1 squared, like this. Now comes the arithmetic grinding, right? I've got here, and where am I supposed to get? Here. So now I need some magic algebra to take me from here to here. So I'm looking at those things, damn, this is what I am, and this is what I'm trying to get. Things must happen nicely for me to get there. So there are many ways to do this kind of thing fast. There are many ways to do them wrong, and usually fast it correlates with wrong. But it comes down to how much experience you have with grinding. This is not an induction thing. It's saying this is the same as that for any n. Now one way is to open all those parentheses. They're both polynomials in the second degree. Two polynomials to be equal, they must have the same exact coefficients. That's the most, like systematic method. Another way is to play with this, to kind of manipulate the terms and say, because I know a lot of math, I can see that this thing here is a 2, this is a 2n plus 1 minus 1, except the first part. And then 2n plus 1 plus 1. This whole interior is still n plus 1 by 3 inside there. So n plus 1 by 3 is n plus 1 by 3. Now this is a squared minus b squared, where a squared is 2n plus 1. You guys know that formula, a squared minus b squared? What is it? Right, so I'm looking at this and I'm seeing n plus 1 by 3. I see an a squared here, which is 2 times n plus 1, everything squared. And I see a 1 that's also squared. So I'm thinking about it this way. Now in here, I'm looking at this, and I also see an a squared minus b squared, which is 2n plus 1 times 2n minus 1 with an n by 3, plus 2n plus 1 squared, right? Now I see a common factor 2n plus 1. I'm going to keep the 3 in here because I need it. I don't want to lose this 3 because this remains here. And now, what have I got in here? 2n plus 1 is the common factor, so I got an n times 2n minus 1. That is 2n squared minus n. n times 2n minus 1. Plus from this other side, I have a 2n plus 1. Am I getting close? So far, what did I get? 3 is the 3, right? 2n plus 1, is there a 2n plus 1 in here somewhere? In this n plus 1 by 3 times this times that, is there a 2n plus 1? Which one is the 2n plus 1?
The first one.
2 times n plus 1 minus 1, I think that's 2n plus 1. That is this guy here, right? So then I need the n plus 1 and this one to be this one here. Hands up who's following me. You don't have to do it this way. There are other ways to do this. Like I said, you can open up all the polynomials and find out that the coefficients are the same. So what do we have here? This is 2n plus 1 by 3 times 2n squared plus n plus 1, which is 2n plus 1 by 3, n plus 1 times 2 n plus 3. That's what I have here, 2n plus 2 plus 1. That's not true. That's fine. I made a mistake somewhere. See that? What is in here is a 2n plus 3, but I don't have a 2n plus 3 in here because I made a mistake somewhere. Where's the mistake? Yes.
When you took out the, so you took out
Louder,
the three
please.
from both- when you took out the 3 from both of them, the second,
This?
yeah, the second one
So
doesn't
it's a
have
common
three.
factor, and I've got the 3 here, I got a 2n plus 1 here.
Yeah,
But from the second one, I've got a 2n plus 1,
but not a 3.
but not the 3 that I forced as a common factor. So, what should I do?
Multiply by 3.
I have a 3 here because I forced out the 3 which was not there. So I have to put it back in. Right? So how is this going to look then? Is 2n squared. How many n's I have total? Minus 1 plus 6. 5n. And then I have plus 3. Now do I get the answer I want? n plus 1 times 2n plus 1, 2n squared plus 3n plus 2n, that's 5n, right? n times 3, 2n, that's 5n, and 3 times 1 is 3. Yes.
Are you missing a 2n plus 1 squared inside of it?
Here?
Yeah.
No, because this was a square, but one with that common factor, one of them.
Oh, yeah.
So again, what happened here? I did a common factor 2n plus 1 divided by 3. Here it is. From the first, I got n and 2n minus 1, which is 2n squared minus n. From the second one, I've left the 2n plus 1, and I have to put the 3 back, which I took out. And now I think this is exactly what I want here. So I've done the induction step proof, which proves the whole chain of implications. Are you guys following this? Hands up with me on this. Okay? That's not the only way to do this. Some people do it, open up all the parentheses here, open up everything here, and say, okay, those two things must be equal. What's the base case? Base case? The way to determine the base case is to look at this chain of implications. You may have multiple chains in there. Everything that doesn't have the arrow into it must be a base case. Because from this P of 1, I can prove everything else. But P of 1 cannot be proven by induction step, because there's no arrow to it. So who's the base case? P of 1. What is that? What is P of 1? Sum from k equal 1 to 1 of 2k minus 1 squared has to be equal with 1 times 4 1 squared minus 1 divided by 3. I just literally wrote this equation for 1. That's what I did. Right. How much is this thing in here? It is only one term, right? And how much is that term? 2 times 1 minus 1 squared. 1. How much is this? 4 times 1 minus 1 is 3 divided by 3. That's 1 times the 1 equal 1. Done. So base case means replace n with 1 in this case. And check out manually that is true. If I were you, I would do the base cases after the induction step, to be clear which ones are base cases, because once you see the chain, you say, okay, P of 1 is the base case. It's easier than doing the base cases first, but most books and mathematical treatments and lectures you see tutorials who do the base cases first. It's totally fine to do them first, but it's hard to tell which ones are the best cases before you see the induction steps. I'm going to show you some problems today where P of 1 is not the base case. So to determine which base case you need, it's much better to see the chain of implications first. All right. Let's do another one. How about, that's problem 2 here today. Let's do a sum of n is a sum from k equal 1 to n of k times k factorial. And the statement is prove that this sum is n plus 1 factorial minus 1. That's what we want to prove. So that's automatically, that's my P of n. I want to prove that for every n, yes.
Quick question. Wait, why is, so did you ever specify the difference between weak induction and strong induction, or do I care?
You don't have to specify it. It's better for readability. If somebody reads what you write to specify it. It's like showing the plan. Weak induction is I'm going from n to n plus 1. Everything other than that is not weak. So if I go from n minus 1 to n plus 1, or if I go from n by 2 to n, or if I go from n by 2 and n by 4 and n by 6 and n minus 1 to n, all of those are not weak. Weak is only n to n plus 1, or n minus 1 to n, depending how you write it. I'd say it's easier to specify it for the TAs. TAs are not mathematicians, like undoubtedly you already know. But it's not required. That's my P of n right here. What's the induction step? Again, I'm stating the step before proving to be clear. What am I proving? So if sum of k equal 1 to n of k times k factorial is indeed n plus 1 factorial minus 1, then that's P of n here. Who is P of n plus 1? Sum from k equal 1 to n plus 1 of k times k factorial, those are the same terms, but like before, the sum has an additional term for n plus 1, is now what is this for n plus 1? N plus 2 factorial minus 1. This is a very similar problem because, sum, it's always the previous sum plus an extra term, right? So let's do this proof. I take the new customer, k times k factorial, and I say that's the same as the old customer plus the last term, because this sum is the same as this sum, but it has an additional term, which is the term for k equal n plus 1, right? It's the previous sum up to n, plus one more term, which is this for n plus 1. How much is that for n plus 1? It's n plus 1 times n plus 1 factorial, right? Because the term for k equal n plus 1 would be this. Now, of course, I use the induction hypothesis. I already know this from the induction hypothesis. That's why I related to the previous sum, because previous sum, it's already known to be that. So now if I put that in there, n plus 1 factorial minus 1 plus n plus 1 times n plus 1 factorial. So this is the induction hypothesis, and this is the same as before. Now what do I see here? I see an n plus 1 factorial common factor. From this, I've got a 1. From this, I've got an n plus 1. And I still have a minus 1 that sticks in there. Again, I did common factor n plus 1 factorial. That's in the front. From this term, I have a nothing left, 1, because n plus 1 factorial is the common factor. From this term, I've got an n plus 1, right? Because it was the common factor times n plus 1, and the minus 1 is this minus 1 here. Now, how much is this? Isn't this n plus 2 factorial? N plus 1 factorial times this whole thing in here is how much? N plus 2. N plus 2 multiplied with n plus 1 factorial is n plus 2 factorial, right? Or wrong? That's done, right? Because n plus 2 factorial minus 1 is exactly what I want to get. Hands up, who's with me? Okay, questions? We know that, right, n plus 2 factorial is n plus 1 factorial, multiplying all the numbers to n plus 1 times the last one, which is n plus 2. Now, this is the same chain of implications like in here. P of 1 implies P of 2 implies P of 3, so on and so forth. So what's my base case? P of 1, which is the sum from k equal 1 to 1 of 1 times 1 factorial is 1 plus 1 factorial minus 1. Is that true? It's a manual verification. This is only one term, this is 1, and this is, how much is 2 factorial? 2 minus 1. Good. That's our number 2. How about number 3? Here's another sum. It says this sum is 1 times 2 plus 2 times 3 plus 3 times 4. Sorry, that's a different one. 1 times 2 plus 2 times 2 squared plus 3 times 2 cubed plus 4 times 2 to the 4 plus n times 2 to the n. How do I write this concise with a summation? That is the sum from k equal 1 to n of who? Can somebody tell me what's the generic term? Very good. And we want to prove that this sum of n is actually 2 plus n minus 1 2 to the n plus 1. All the sums are easy because the new sum is going to be the old sum plus a term, right? Obviously. So what's the induction step? If the sum of n is indeed 2 plus n minus 1 at 2 of n, 2 to n plus 1, then that's the induction implication. The same has to be true. Sum of n plus 1 has to be, how do I write this for n plus 1? 2 plus n times 2 what? Right? That's this expression here, but not in n plus 1. Now this is of course my p of n, the statement, true or false, and this is my p of n plus 1 statement, true or false. So the induction implication here is still weak induction, n to n plus 1. Now how do we prove this? We start with the new customer. Sum of n plus 1 is who? That's the sum from all k equal 1 to n plus 1 of k times 2 to the k. That is the previous sum plus what's the new term? So this is all the terms up to n, but this sum includes another term, which is the n plus 1. So I need to write manually the term for n plus 1. What is that? N plus 1 to the n plus 1. Now I use the induction hypothesis. I know this. That's why I put it here, the previous sum. I know already that's 2 plus n minus 1, 2 to the n plus 1, right? From induction hypothesis, I know this sum. To which I add my new term, n plus 1 times 2 to the n plus 1. What do I see here? I see the 2, I leave it alone because 2, I need it anyway. So every time I see something that I need, I kind of try to kind of take it out. Because that 2, I need to stay there. Plus, I see a 2 at n plus 1 common factor. What's left from here? N minus 1. And what's left from the other one? Okay? So how much is this? 2 plus 2 at n plus 1. How much is n minus 1 plus n plus 1? 2n. So that's 2n. Is that what I want? 2 is the 2 to n. N is the n. And 2 at n plus 1 times 2 is? This is the same implication. I just proved P of 1 implies P of 2, implies so on and so forth, all of them. Then the base case is this one. Base case. How do we do this for 1? Sum of 1 is the sum from k equal 1 to 1 of k times 2 to the k. That has to be equal, according to the formula, to 2 plus 1 minus 1, 2 to the 1 plus 1. There's only one term here, right? That's 1 times 2 equal 2 plus 0 times 2 to the 2. Is that true? Yes or no? Done. So the base case, I'm just putting k equal 1 or 2, whatever the base case, and I'm checking manually. I'm not worried about how summations work. I'm just saying, if you want to prove this for P of 1, put k equal 1, check it manually if it's true or false. Okay? Again, why do I need P of 1 here? Because the induction step proves all the chain, but I have to start with a true statement. I can't get here the induction step P of 1. Hands up who's with me. Okay, any questions? I know some of you seen inductions before, so I'm counting on that fact more or less here. Okay, number 4. Here's another one. This is not a sum. This is a different thing. Let's call it x of n. This is 1 minus 1/4 times 1 minus 1/9. times 1 minus 1/16 times 1 minus 1 over n squared. Can anybody tell me what is this in concise form? Yes. It's not a sum. It's a product. It's a product. Because these guys are multiplied. From k equal 2 to n. What is inside the product? Like that? Is the first one 2 squared, 3 squared, 4 squared, the last one 10 squared, right? And the proof is this x of n is n plus 1 divided by 2n. Okay? So, can we apply the idea for the sums to the products? Because clearly that's not a sum. But is the new customer, the old customer, and something else? How do I write that? What's the and something else? So this is my E of n statement. What's my induction step here? If this product from k equals 2 to n of 1 minus 1 over k squared is indeed n plus 1 by 2n, then how do I write this statement for the next n plus 1? The product from k equal 2 to, I said product, but I wrote sum, n plus 1 of the same 1 over k squared, it has to be now what? N plus 2 divided by, this is 2n, not 2 to the n. 2 times n plus 1. I'm just replacing n with n plus 1. Now, I start the same proof. The new customer product from k equal 2 to n plus 1 of 1 minus k 1 over k squared. How do I relate this to the previous customer? What is the new customer in relation to the previous customer? Somebody loud.
It's the product of the old customer with the n plus 1.
Is the same product as before with one more factor. In product, the things that you make the product of are factors. In a sum, they are terms. So you can't say times the next term, because terms are in a sum. In a product, you say times of the next factor. So what is the previous one? That is the product for k equal 2 to n of 1 minus 1 over k squared. What is the new thing?
1 minus 1 over n plus 1 squared.
Right. Now I apply the induction hypothesis to this one, which I have here. N plus 1 divided by 2n from the induction hypothesis. Times the new thing. What's the new thing? I'm going to work on this fraction a little bit. Can I write it as n plus 1 squared minus 1 divided by n plus 1 squared? Right, because I kind of multiply this one to n plus 1 squared minus 1 divided by the denominator, right? So what do I have here? How do I work this out? How about take a look at where I'm trying to go? I'm trying to go here. So the 2 is good, right? 2 is here, it's here, good. I have an n plus 1, so this n plus 1 is good, because it's what I already have. So actually the other n plus 1 goes away with this n plus 1. So that's good, I got 2n plus 1. Let's write that down, 1 over 2n plus 1, because these guys, 2 and n plus 1, are what I need there, right? And then what is left? I've got this 1 over n here, right? Because that's n still in there. And now how much is this? I need a formula, a plus b squared. It's what? Loud? N squared plus 2n plus 1, right? Minus 1. because the minus 1 is from here. And this a plus b squared is a squared plus b squared plus 2ab, right? So what happens now? I got 1, go away with minus 1. This is already good. I already checked it, 2n plus 1. That's why I kind of take it out to not have to worry about. Now what I have here is an n plus 2. Is this an n plus 2? If I work on it a little bit, do I get an n plus 2 here? Yes. Done. So what did I prove? It's still P of 1 implies P of 2 implies P of 3, so on and so forth, all of them. Because this is still a weak induction. The properties are different properties, but it's still going from n to n plus 1. I didn't move from that spot yet. So what's the base case? P of 1, which is what? Is it P of 1? How is this sum going? From this product is going from 2 to n. So the P of 1 makes sense here? What is actually the chain that I proved? Is this the correct chain that I proved? No. That's where people lose points. That's not what I proved. I proved this chain starting from where? From 2. I should write that in my induction step. Induction step is P of n implies P of n plus 1 for any n starting at 2. So now that I look at my chain, 2 implies 3 implies 4 implies 5, so on and so forth. Which is the best case? Which one is the best case? 2, this one, the first guy. So who's that? It's 1 minus 1/4 has to equal 2 plus 1 divided by 2 times 2. Is that true? I just replaced n with 2 in there. 1 over 1/4 is the first factor here, and 2 plus 1 divided by 2 times 2. Is this correct? 1 minus 1/4 equal 3/4. Good. Hands up who's with me. This would be the time to ask a question about weak induction. So weak induction, I move from n to n plus 1. I prove it in general, sometimes not starting at 1, maybe it starts at 2, maybe at 3 at some point. And then I have the whole chain proof. The first one in the chain is the base case, but I prove manually. Easy, right? Let's see what else we have here. They're a little bit out of order. Here's an interesting one. We're going to need more than one board for this one. Here's a bunch of things that we can do by induction. Problem 5. It says n factorial is bigger than 3 to the n, is bigger than 2 to the n, it's bigger than n squared, bigger than n log base 2, or the logs here are base 2. And it's bigger than n, it's bigger than log base 2 of n, or all n starting at 7. So this is the kind of thing you already know from when we talk about growth of function. Didn't we say the factorial is bigger than any exponential? An exponential with a bigger base is bigger than an exponential with a smaller base, right? Then how do you actually prove this? Like, I mean, it's one thing to state it makes sense, and quite another thing to prove it. 2 at the end is bigger than n squared. Any exponential is bigger than any polynomial. Eventually, so I set up here starting at 7. N squared is bigger than n log n. That's if I get an n out, that's n bigger than log n, effectively, because it's one n in here goes away with one of these two. And then n log n is bigger than n. That's easy because log n is bigger than 1, right? And then n bigger than this. So let's do it by induction. If this is P of n right here, if I know all these inequalities, then I know the P of n plus 1. N plus 1 factorial is bigger than 3 at n plus 1. It's bigger than 2 at n plus 1. It's bigger than n plus 1 square. It's bigger than n plus 1 log of n plus 1. I'm not going to write log base 2. All the logs are base 2 in here. It's bigger than n plus 1. It's bigger than log of n plus 1. So I put n in there. Now that's my P of n plus 1. So my induction statement is still weak induction. Now the property involves 6 inequalities, or however many. Yet if these all are true, then the other ones are true. I'm going to prove it. N plus 1 factorial is n factorial times n plus 1, which is, I apply induction hypothesis here between n factorial and 3 to the n. This is bigger than 3 to the n times n plus 1. N factorial is bigger than 3 to the n. I know this from the induction hypothesis. This is bigger than 3 to the n times 3 because n plus 1 is bigger than 3, which is 3 to the n plus 1, of course, which is, I'm just going to write here, 3 to the n plus 1. Now 3 to the n times 3 is bigger than 2 to the n times 3. This is another induction hypothesis. So when I use induction hypothesis, when I say n factorial is bigger than 2 to the n, that's in here. Another one is saying 3 to the n is bigger than 2 to the n, that's in here. Now this is bigger than 2 to the n times 2. That's not induction hypothesis, just say 3 is bigger than 2. That's, of course, is 2 to the n plus 1. So far, I've already proved that n plus 1 factorial is bigger than 3 to the n plus 1, is bigger than 2 to the n plus 1. So I'm done with this part, up to here. Again, how that went, I went to the n plus 1 factorial, that's n factorial times n plus 1. N factorial is bigger than 3 to the n, that's induction hypothesis. 3 to the n, n plus 1 is bigger than 3 to the n times 3. That's because n plus 1 is bigger than 3, because n is at least 7. So this n plus 1 is at least 8. It's bigger than 3. 3 to the n is bigger than 2 to the n. That's induction hypothesis times 3. 3 is bigger than 2, so that's 2 to the n plus 1. Now how about this one here? I want to prove this. So 2 to the n plus 1 is 2 to the n times 2. Now I apply the induction hypothesis. 2 to the n is bigger than n squared. Right? Which is equal with n squared plus n squared, because there's 2 of them, which is equal to n squared is bigger than. So let's see how this went. 2 to the n plus 1 is 2 to the n times 2. 2 to the n is bigger than n squared. That's induction hypothesis. N squared times 2 is n squared plus n squared. N squared stays. N squared is bigger than 7n. Why is that?
N is bigger than 7.
N is at least 7. Now 7n is 2n plus 5n. I need a 2n in this formula here. And 5n is bigger than 1. Now this is exactly n plus 1 squared. So that's now proving that 2 to the n plus 1, I just proved this one here. Here's the last one. Two to the n plus 1 is greater than n squared. Therefore, n plus 1, I take the logs here, is bigger than log of n squared, which is 2 log of n. My note says something different here. This is bigger than log of 7n. Let's see how this one went. 2 to the n plus 1 is bigger than n squared. I've already proved this. So then n plus 1 is bigger than the log of n squared. Now, how did I went from log of n squared to log of 7n? N is more than 7. 7n is n plus 6n. I need n plus 1. 6n is bigger than 1. So that's that one. And then I've done this one. I have to do those two. N plus 1 is greater than log of n plus 1. What do we want to prove here? We want to prove this and that. So, but I use this one which I just proved in here. Then n plus 1 squared is bigger than n plus 1 times log of n plus 1, which is bigger than n plus 1 times log of 7, which is bigger than n plus 1. This one is the inequality I just proved line before. How did I get from here to here? From here to here. What did I do? I multiply by n plus 1 both sides. This n plus 1 squared, this n plus 1 times log n plus 1. Now from here to here, n plus 1 is n plus 1. Can I say log n plus 1 is log 7, more than log 7? Because then it's at least 7. So now log 7 to get to n plus 1 is bigger than n plus 1. I need log 7 to be bigger than 1, which is true, right? So that proves the remaining two inequalities, that n plus 1 squared is bigger than this, bigger than n plus 1. So now I proved all the 6 inequalities in the n plus 1 step. I need base case, right? This is still a weak induction. I'm going from n to n plus 1. And what would be my base case? It's n equals 7, right? So in n equals 7, I need to prove 7 factorial is bigger than 3 to the 7, bigger than 2 to the 7, bigger than 7 squared, bigger than 7 log 7, bigger than 7, bigger than log of 7. And that can be checked manually with the calculator. Okay? Now, I know this, we already know this property, but now you know extremely formal why they are true without calculus. We can do a lot of proofs with calculus and L'Hopital rules, but see, with induction, I can prove this for natural numbers. Of course, these inequalities are also true for non-natural numbers, like real numbers. 3 to the x is bigger than 2 to the x, bigger than x squared, so on and so forth. But here's a proof for the natural numbers. And that was number 5. Number 6. It's an old friend of ours, number 6. It says x plus y to the n is the sum from k equals 0 to n of who? N choose k, x to the k, 1 to n minus k. Guys, remember this one? Binomial theorem? How did we prove it? We did a sort of a proof, not very rigorous, that was saying, if you look at x plus y n parentheses, to get a particular combination of x and y's, no matter how you, when you open them, you're gonna get some x's times some y's. And if you look at exactly kx's and n minus ky's, it means pick, in k parentheses, pick the x, and in the other n minus k parentheses, pick the y. And how many ways can I do that? Well, I have to pick the parentheses for the x, that's n choose k, and that's how I get this out. That was correct, but kind of informal. We're gonna do this by, this is P of n. So I wanna prove this by induction on n. So this is the induction step right here. Who's P of n plus 1? How do I write the thing for P of n plus 1? Sum from k equals 0 to n plus 1.
Plus one.
N plus 1 choose k, x to the k, y to what power?
N plus one.
So I'll prove this by induction, and I remember a Pascal thing here. N plus 1 choose k is n choose k plus n choose k minus 1. Remember that? That's how Pascal triangle works. When you get the next guy, you sum up the one before, which are exactly n choose k and n choose k minus 1. We did a proof of this. We said if you want to choose out of this n plus 1 students, k of them, you have two options. Either choose her or not choose her. She's a particular student. If I choose her, I have one already student chosen, right? And I have to choose the rest of k minus 1 out of the rest of n students. If in this class it's n plus 1 students, and she's already in the chosen k, then out of the rest of the students, I have to choose the rest of k minus 1 students. The other way is to not include her in the chosen k. And then I have to choose all k out of the remaining students. So it's that plus that, these joint cases, so it's some rule at the moment. Okay? So how do we do this? This has to be x plus y at n plus 1, right? Because it says if this x plus y at n is that, x plus y at n plus 1 is that. Let's prove this thing. I start with, this is my customer here. I could start with this customer, but my note says start with this customer here. So who's x plus y? How do I relate x plus y at power n plus 1 with the previous customer? Yes?
X plus y to the n times x plus y.
Times x plus y, right? Now I know who x plus y to the n is this formula. So this is going to be x times that formula, sum from k equals 0 to n of n choose k, x to the k, y, n minus k. X is from this x here. The formula is that times x plus y, this is the y from here, times the same formula. Now, I'm thinking I can bring these x's inside. So this x multiplied with this bunch of x's here will give me x at what power? K plus 1. And this y will multiply with this bunch of y's here will be n minus k plus 1. Right? But I want to write separately two terms. So two terms. In here is the k equal n term. I want to write that separately. K equal n gives me what? The whole thing is what? When k is n. What do I get here? X to the n. So x to the n times x, that's x to the n plus 1. And from the other formula, I'm going to put a parenthesis here. That was k equal n. And the rest of it is sum from k equals 0 to n minus 1, right? Because I already took out the term for k equal n. So the remaining terms are from 0 to n minus 1. I've got n choose k, x to the k plus 1, y n plus 1 minus k. Right? Again, what happened here? This sum, I took out one term out of it for k equal n. For k equal n, that's x to the n multiplied with x, that was x to n plus 1. The rest of it is the whole sum from k, not to the n, because the n term is out, k 0 to n minus 1. And I multiplied this x with all the x's inside to get x to k plus 1. Hands up who's with me here. I do the same in there. This is going to be the sum from k equal 1 to n of n choose k, x to the k, y to the n plus 1 minus k. Where is n plus 1 minus k coming from? Where? Why do I have here a 1 plus 1 minus n plus 1 minus k? Yes.
Because you multiply the whole product.
I multiplied this y, I put it inside. Now my sum is from k equal to 1 to n, so I'm missing a term. I'm missing the k equals 0 term. K equals 0, this sum will be what? This term will be what? Y to the n times another y. Y to the n plus 1. Okay? So now I have these two guys together, x at n plus 1 plus y at n plus 1, those two separate ones, plus I'm going to keep this sum the way it is. I want to change the indexing of this sum. K runs from 0 to n minus 1. I want this sum to run from k equal 1 to n instead. It's the same exact terms, but instead of indexing from 0, I index from 1. But I want to make sure what I write is exactly the same. So if this is indexed from 1 instead of 0, who would this be? If my old k has to be now related to the new k, how do I change the indexing here? This has to be instead of k what?
K minus 1.
K minus 1. And the x is at what power here? K, right? Because now k is 1 above what it was before. So k plus 1 is the new k. And y has to be what? I think it's like that, right?
Oh.
If k plus 1 becomes k becomes k minus 1, minus k becomes minus k plus 1, plus k equal 1 to n, this stays the same. Now what do I notice? These two are the same exact x at k 1 n minus k plus 1. This one here and this one here are the same. I can group those sums together term by term because they have the same summation 1 to n, 1 to n. This expression x at k, y at n minus k plus 1 is the same, x at k, y at n plus 1 minus k, right? So I'm going to group those two together. I'm going to get x at n plus 1 plus y at n plus 1 plus a big sum here, k equal 1 to n. When I group these together, xk, y at n plus 1 minus k, the common factor, this is going to be now n choose k minus 1 plus n choose k. N choose k minus 1 comes from here, n choose k comes from here. So every pair of two terms got a common factor, and my Pascal friend here, the sum of those two n choose k, right? This one is from here, this one is from here. So this is now x at n plus 1 plus y at n plus 1 plus this sum, k equal 1 to n. How much we said is this? This is a Pascal formula right here. Right? So instead of that sum of two n choose k, I have n plus 1 choose k instead of this parenthesis, times x at k, y at n plus 1 minus k. Now I'm gonna say, if you look at this sum, runs from 1 to n. But what is the k equals 0 for this sum? So this sum is from 1 to n. But if I am to imagine a term that's for k equals 0, what would I get here? So if I put k equals 0, what this is? Y at? That is here, that's the k equals 0 term for this sum. How about if I put n plus 1? If I put inside the sum n plus 1, n plus 1 choose n plus 1 is 1. X at n plus 1, y at, I'm putting k equal n plus 1. So that's, this guy in here is the k equal n plus 1 for that sum. So this is the sum from 1 to n, plus two other terms for k equals 0 and k equal n plus 1 written separately. So that is the sum now from k equals 0 to n plus 1. N plus 1 choose k, x to the k, y to n plus 1 minus k. I think that's it. That's exactly the formula we wanted to prove. Okay? Induction step. Of course, we need to prove a base case. This is still a weak induction. It's from P of n to Pn plus 1. P of n is complicated, but the induction step is still from n to n plus 1. Hands up who's with me. Be honest. What's the base case? N equal 1, right? That needs to be x plus y at 1 has to be the sum from k equals 0 to 1 of n choose k, x at k, y at n minus k, right? That's exactly x plus y. And now there's two terms in this sum. One of them is x, the other one is y. So that's the base case. Okay, so we prove binomial theorem with induction. Next one, we prove a bunch of inequalities. I want to do more inequalities very soon. Here's another one. Oh, we can do this one here. It's very small. Number 7. Number 7, I want to prove that 5 divides a to the n minus 3 to the n for any n starting at 0. Yes?
Wait, real quick, you know number 5?
5?
Yeah, in proof 5.
Yeah.
How did you get from, or how did you get to 3n times n plus 1?
Here?
Yeah, how did you get that?
So I say n plus 1 is n plus 1.
Okay.
And n factorial is bigger than 3 to the n.
Yeah.
So the n plus 1 is the same. I just say n factorial is bigger than 3 to the n, right?
Yeah, but I'm looking at the previous thing right above that.
So this one is clear.
Okay.
But what's the question?
Where did you pull that from?
Where did I get n factorial is bigger than 3 to the n?
No, not that. So you just have n plus 1. Like, where did you pull the 3n to the n? Is that from your 3 to the n plus 1 term?
So n plus 1 remains n plus 1.
Yeah, yeah.
I just replace n factorial with 3 to the n.
Why?
Because I know this from here.
Okay.
Now I think maybe you want to ask, how did you come up with this thing? Like, okay, every step makes sense, but how did you come up with it? There was a lot of trial and error last year. That was the problem. It's proved by induction. And everybody knew it's true. Everybody was scrambling up to say, okay, well, how do you actually do it? So after many trials and error, we've got this plan.
Okay.
But this is induction hypothesis here. N factorial bigger than 3 to the n. We assume that we know that and want to prove it. Okay. I want to prove this one now. This, yes.
Can you show proof 6 again? Like, raise the right click. Thank you.
How many people are still following this one? It's a beautiful record. All right. Let's do this one very quick. That's my P of n. So this is the induction step. Who is P of n plus 1? If this is P of n. 5 divides. Right? How do I prove this? I start with my new customer, which of course is not the 5, because 5 is the same. Who is the new customer here? My new customer, 8 at n plus 1 minus 3 at n plus 1, I need to relate this to the previous customer. How do I do that? Is there an obvious relationship between this and that? That's the issue in this problem. A lot of people will say, okay, well, that sounds like related, right? Like, it's not a sum, it's not a product, it's a difference between the next powers, right? But how do I write mathematically? I have to relate the new customer with the old customer. Yes?
There's some multiple of 5 too.
What?
There would need to be a multiple of 5 between 8 and minus 3 and 8.
That's what I want to show, that it's a multiple of 5.
Yeah, but between them.
But they obviously, neither of them is a multiple of 5. It's 8 at the power and 3 at the power are not multiples of 5.
Well, like, no, between the 8 and minus 3 and 10.
Right, this is a multiple of 5 by induction hypothesis. I know that. But now I have to relate the new one to the old one. So how do I do that? What's the relation? How do I write that with math? To get this to relate to that. Well, what's the relationship between 8 at n plus 1 versus 8 to the n? 8 times 8 to the n minus 3 times 3 to the n. Am I getting close here? How do I get from here to the previous customer? I need to break this 8 to the n orange. I have 8 of them. I need to break it into parts. How many oranges do I need to get my previous customer? So I'm looking at 8 to the n, and there's 8 of them. That's too many. I only need, in order to get here a nice 8 to the n minus 3 to the n inside the common factor. Yes. I want to do 3 of 8 to the n minus 3 times 3 to the n, because I see this way I'm going to get close to my old customer there. But of course, I have to now put back the other ones, right? So how many oranges I have left? 3 went here. I had 8 to start with. So now I have 5 times 8 to the n. Now if I do common factor here, what do I get? 3 times 8 to the n minus 3 to the n plus 5 times 8 to the n. Now I apply the induction hypothesis that says this is a multiple of 5. So that's 5k. So that is going to be 3 times 5k plus 5 times 8 to the n. This is a multiple of 5, right? Because I see 5 here, 5 here. I need a base case, you guys do that. Because this is still a weak induction, n to n plus 1. You just have to prove it for, you can do multiple base cases to be sure. N equals 0, n equals 1, n equals 2, few base cases. You only need one of them, n equals 0. But if you do 2 or 3, that's fine. The advantage to start with base cases is to get the feel of the problem. Try it out to see how it works. I think in proof, when you write the proof, it's better to write the base cases at the end, like I said, to know exactly which ones you need. But if you want to try it out, hey, what a magic thing, I never seen this before. Let's try n equals 3, just to see, is it true or not? You can do that. So that is number 7. After 7 comes 8. H2 of n. This was in the homework but got taken out. Because apparently it's too hard, but it's not hard at all. You'll see. It's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over n squared. It's less than 2 for any n. So that's P of n. That this is less than 2. We want to prove that no matter how many times you add squares in here, you can never beat 2. The real difficulty in here is that I can't really prove 2 because 2 is a constant. Inductively, constants are not good. If I say this is smaller than 2, as soon as I add something to it, think how induction is going to work. My h2 of n plus 1, who's that going to be? It's a sum which is the previous sum plus another term, right? It's 1 over 1 squared plus 1 over 2 squared plus 1 over n plus 1 squared, which is the same sum as before, h2 of n, plus what's the next term here? 1 over n plus 1 squared. The problem with inequalities with constants, if this is smaller than 2, and I use that induction hypothesis here to say that's smaller than 2, it can't possibly be still smaller than 2 if I add something to it, right? I mean, the proof won't work that way. Everybody follows me here? If I just use it like that, once I put it here, if that's less than 2, if I add something, I cannot prove it's still less than 2 because this something adds to that value. The trick in here is to say this is smaller than 2 minus 1 over n, which of course it's even stronger than the original statement, right? Because if it's stronger than, if it's less than this, that's certainly less than 2, right? So now this will be, I want to prove that this is smaller than what? Because the statement has to be consistent. If this is P of n now, who's P of n plus 1? How do I write this n here with
2 minus 1 over n.
right? Well, let's try that. So I start with a new customer, h2 of n plus 1, proof. So this is the induction step right here. If this, then that, it's still weak induction. It's from n to n plus 1. h2 plus 1 is the same as h2 of n plus 1 over n plus 1 squared. Now I know this is smaller than 2 minus 1 over n plus 1 over n plus 1 squared, right? Because I know this is smaller than 2 1 over minus 1 over n. I'm adding 1 over n plus 1 squared to it. You guys should know inequality here, which is saying 1 over n plus 1 squared is smaller than 1 over n times n plus 1. Is that true? If I decrease the denominator, I increase the fraction. Right? This is n plus 1 times n plus 1, that's n plus 1 times n. It's smaller, therefore the fraction is bigger. And now another thing that you need to know is this is 1 over n minus 1 over n plus 1. That's easy to see because if you do the to get the same denominator, n plus 1 minus n times that. So I'm going to say this one here, I apply the inequality. I have 1 over n plus 1 squared. This is 2 minus 1 over n. I make it bigger by using this instead, which is this. So let's do it step by step, n plus 1. Now this is 2 minus 1 over n plus 1 over n minus 1 plus 1, right? Guess what happens here? 1 over n goes away, 1 over n. That's 2 minus 1 over n plus 1. Done. So how does this work? Again, step by step. The new customer is the previous customer plus another term. This, it's smaller than this. So I can keep going. With inequalities, they have to go in the same direction. Once you use smaller than, all inequalities have to be smaller than because they're transitive in one direction. So smaller than, I keep the This is from the induction hypothesis, this to this. This H2 of n, it's known to be smaller than 2 minus 1 over n, induction hypothesis. 1 over n plus 1 squared. Now this, it's smaller than 1 divided by n times n plus 1. That's in here. 1 over n times n plus 1 becomes 1 over n minus 1 over n plus 1. This is nice now because 1 over n goes away with 1 over n. And I'm left to 2 minus. Is that correct? 2 minus 1 over n plus 1 here? So I need the base case. H2 of 1 is 1. It's smaller or equal than 2 minus 1 over 1. Is that true? 1 smaller or equal than 2 minus 1 over 1. True. Now, there is another way to do this series. I showed you the inductive way. Here's the telescoping way. It's a technique that's quite useful. Telescoping series. Refers to something like this one in here. If xn is an minus d minus an plus 1. If I want to sum up a bunch of terms, each one of them is a difference of consecutive terms from another series. The sum of xk, it's going to be a1 minus a2 plus a2 minus a3 plus a3 minus a4, so on and so forth, plus the last one is going to be an from k equal 1 to n minus an plus 1. In a telescoping series, the terms reduce one to another, and you left the first minus the last. That's exactly how this series can be proven. Using this thing in here, we notice that now sum over 1 over n squared, which is our k squared, h2 of n, it's smaller than sum over 1 over k times k minus 1, I think. I have to leave the 1 alone, so I'm going to start this one from 2 to n, and I have to write the 1 separately, 1 plus. Because I can't put 1 times 0 here, it won't work, the denominator. Now if I write this sum as 1 over 1, so the 1 in the front is fine, plus this is 1 over 1 minus 1 over 2, plus 1 over 2 minus 1 over 3, plus 1 over 3 minus 1 over 4, so on and so forth. The last one is 1 over n minus 1 over n minus 1 minus 1 over n. Telescoping means this goes away with this, that with that, that with that, so on and so forth. So the end result is the one I have plus the first one here that remains 1 minus 1 over n. So that's 2 minus 1 over n. The principle of a telescoping series is the observation, this one here. I want to sum a bunch of terms, but every one of them is a difference of the n versus n plus 1 in another series. In a telescoping, they will always cancel out when you add up a bunch of these terms.
Wait, so can you go back to your induction hypothesis?
This induction here?
Yeah. So you were given that harmonic series is less than 2, right?
Yeah.
And then you're saying that was what you were given, but you changed it to be more specific so that it's less than 2.
Right, because constants don't work with inequalities.
But
by
you weren't
induction.
given that. You have to.
Right, you have to come up with that.
Okay.
The way I come up with it is because I knew the telescoping property.
Okay.
Using this in here, I knew I can get it to 2 minus 1 over n. So it's very hard to have this creative idea if you don't know how to go by it, because with 2 you can't prove it by induction. As soon as you add something to 2, it's more than 2.
That was your creative step.
But this way, it's easier to think about it first. If you get into telescope, a lot of terms reduce, you get 1 minus 1 over n plus the 1 in the front. Okay. How about strong induction? Strong induction is not P of n implies P of n plus 1. It's all the previous P's. P of 1, P of 2, P of 3, up to P of n. All of them implies P of n plus 1. Or some of them. So in strong induction, we're not just proving from n is n plus 1. We still have this chain, but to prove the Pn plus 1, we need all the statements from before. And then we have to figure out base cases, which might depend on how exactly the chaining works. So here's, I have a problem here. Which number are we at? Number 9. Number 9, 10 at any power is a sum of 2 squares. 2 integer squares, of course, that's what I mean. That's my P of n. So the induction step, if I try weak induction, I'm going to be like, okay, 10 at n plus 1 is some other square, c squared plus d squared. Those are generic integers, like the k I used before. When I say a, b, c, d, I mean any integer. I don't mean a specific a. So if I try this proof, I'd say, okay, proof. This, how do I relate my new customer to the old customer? Who's 10 at n plus 1? In relation to 10 to the n. 10 to the n times 10, right? We all know this. Now I use the induction hypothesis. Who is this? A squared plus b squared times 10. Now I'm looking at where I am and where I want to go, and I'm like, okay, is a squared plus b squared times 10 is sum of 2 squares? Can you make that happen? Very questionable that a squared plus b squared times 10 is the sum of 2 squares. I mean, who knows? It seems hard to prove. So what do I do? Did I show you yesterday this? So what do I do? Yes.
Can you say it's 9 times 10 to the n plus 9 squared times 10 to the n minus 1 dot 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 dot? Because 9 is 3 squared, so then you like a squared plus b squared times 3 squared, which is the sum of 2 squares.
So you're saying this is what? 9 plus 1?
Yeah.
And then I get 9a squares plus 9b squares plus a squared plus b squared?
No, and then a squared plus b squared is 10 to the n, and then you repeat that, so you get, as you can repeat all of them.
I don't know if that works. I mean, maybe. Here's an idea. How about an easier idea? Maybe his one works too. How about I move from P of n to P of n plus 2? So that's not n plus 1, it's n plus 2. Would that work? Who's n plus 2 in relation to 2 to the n? Times 10 squared. Now a squared times plus b squared times 10 squared. Would that be a sum of squares? Would it?
Yeah.
What are the squares? 10a squared plus 10b squared. Right? Hands up who's with me. It didn't work from n to n plus 1, but it did work very easily from n to n plus 2 in here. So what did I actually prove if I write down my chain I want to see? From P of 1, where did I get? P of 3. From P of 3 I get to P of 5. From P of 5 I get to P of so on and so forth. And from P of 2 I get to where? P of 4. From P of 4, P of 6. From P of 6 I get to P of 8. Are those all the cases included here? Are all integers already in this chain? So which ones are my base cases here? Which one? These are base cases because there's nothing implying them. I can't get 1 and 2. Clearly in this chain everything else is implied, but not 1 and 2. So let's do this manually. N equal 1, 10 at 1 is the sum of 2 squares. 3 squared plus 1 squared. How about n equal 2? Is 100 sum of 2 squares? 6 squared plus 8 squared. So the base cases work. I have 2 chains of implications here. And this is not a weak induction because it's not from n to n plus 1. It's from n to n plus 2, or from n minus 1 to n plus 1, depending how you index it. All right? Easy, right? So this is a strong induction. Because it's not n to n plus 1. What else we have here? That's number 9. How about number 10? Number 10. If n is greater than 12 cents, that's change with coins. There is a way to give change with coins of 4 cents and 5 cents. So if I have my coins are only 4 cents and 5 cents, I can make change with those coins for any n starting at 12. So before I even start the induction steps, I wanna kind of get the feeling for how this problem goes. So I'm not doing the induction just yet. I'm just thinking about the problem, and I'm saying what's the obvious change I can give with those coins? The basic cases that if I just use one coin, what can I do? I have a coin of 4 cents and one of 5 cents. So can I do what? 4 cents, right? That's using one coin of 4 cents. That's 4. And from 4, and this is 5, that's one coin of 5 cents. From 4, if I add another 4, what do I do? I can do 8. If I add another 5, I can do 9. From this, I can also do 9, adding a 4. If I add a 5 to it, and from 8, if I add another 4, 12. From 8, if I add a 5, 13. From 9, if I add a 4, that's 14. From 9, if I add a 5, 14. From 10, if I add a 4, 14. From 10, if I add a 5. So it looks like in the beginning, the base cases are complicated. Clearly, I can do the 4 cents, 5 cents, 8, 9, 10, 12, 13, 14, 15. There's some numbers missing here that cannot be realized if my thinking is correct. Can I do 6, 7, 8, 9, 10, how about 11? No, it looks like those are impossible. But that's okay, because it's starting from 12, right? I don't need to worry about numbers below 12. So my thinking is, this is how the base cases will work. It's not a proof yet. It's a base case. But what I get out of this is that I can do 12, 13, 14, and 15. And from here, I think I got an induction step. Here's my induction step. If you can do at least starting at 12, 13, 14, and 15, then you can certainly do adding 4 to it, right? Because I had another coin of 4, P of n plus 4. So the reason that's enough is because by having 12, 13, 14, and 15, what happens if I add a 4 to 12? I get the next one. To 13, next one. 14, next one. 15, next one, right? So if I got those 4, from here adding 4 to it, I get to every natural number. But I needed this kind of thinking before to decide, okay, how can I come up with this induction step if I don't look into this beginning of the picture? So this is easy to prove, right? This is obvious. In this problem, it doesn't need a proof. If you can do coin for n cents, how do you change for n cents? How do you do n plus 4? You add a coin of size 4 cents to it, right? Add 4 cents coin. So now that I'm looking at my chains, I've got P of 12 implies P of 16 implies all of them. P of 13 implies P of 17 implies P of 21, all of them. P of 14, P of 18, P of 22, and P of 15, P of 19, P of 23, all of them. Would that include all the integers here? I think so. So I'm looking at this. These are my base cases. I think it would have been difficult in the beginning of this problem to say, without looking at all this thinking, 12, 13, 14, and 15 are your base cases. But now that we see how this works here, this is kind of scrap paper. How do I think about the problem? Then I see the induction steps. The induction step, it's easy. It's no proof at all. If you can do n, you can do n plus 4. You just add a coin to it. You see these chains. You know these are the base cases, which you can do either based on the scrap, but you can do manually, right? Who is 12? 3 times 4 cents. Who is 13? 2 times 4 cents plus 1 times 5 cents, etc. So you can do this manually just to show you can give cents to them, and then the induction takes care of the rest. There are 4 chains going on here. You can solve this problem using the 5 coin. There will be a different induction step and different chains. But I think that's the easiest way to think about it. Yes?
Is it possible to show that this is true for any 2 coins that are 1 cent apart for a sufficiently large n?
Actually, I have a more interesting question. What property the 2 coins need to have for that to be true? So if I give you 2 coins A and B, A, B are 2 integers. In what case there is an n0, doesn't matter what it is, but there is a starting point. After that, all the integers can be done with them.
Relatively high.
Yes. Very good. All right. So that was number 10. I don't think we're going to do 15 today. But we can do a few more. Right? Where is 11 here? Oh.
Take 9 squared, right? Normal number, right? Actually, and
Use the mirror. Mirror 9-degree vertex base on the side. Marxist.
So number 11. If I have n lines
Function.
in plane,
okay, John discovered this.
no, like n lines, how many lines are here? 4. That's going to result in n squared plus n plus 2 divided by 2 regions of Regions, I mean partition. So how many regions are here? Let's call them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 11 too? Is that true? So what was my n here? This is the scrap paper. N was, how many lines I got? 4. How much is 4 squared plus 4 plus 2 divided by 2? Is it 11? Is it 11 or not?
Yes.
There you go, the base case. It works. Right. No lines are parallel and no lines are concurrent. 3 of them passing to the same point. No parallel, no concurrent. Like all 3 passing to one point. Okay, so this is a base case, of course, if I need it, because I just prove it for n equals 4. But how does this work in general? Well, what is my P of n plus 1? This is P of n. P of n plus 1 will be what? N plus 1 lines generate how many regions? How do I write this formula for n plus 1? N plus 1 squared plus n plus 1 plus 2 divided by 2 regions. How do I think of such a problem? If you got n plus 1 lines, I need to relate the next customer to the previous customer, remember? What's my next customer here?
The field, yeah, the extra line. So
I have n plus 1 lines. How do I relate that to n lines? Yes.
if you have an plus 1 lines, you know that a plus 1 line is intersecting a lines.
Right.
And acts on which.
So here's what he's saying. Look at the n plus 1 line. And look at the other n lines. Right? Now, n lines. This is the n plus 1 line. N lines create how many regions? By the induction hypothesis. N squared plus n plus 2 divided by 2 regions. Now, that was before putting the n plus 1 line in. It's just with n lines. Now I add the n plus 1 line in. How many intersection n plus 1 line has with the other lines? N intersections, right? Is it true that every intersection splits an existing region into 2? Is that correct? Why is that? Like in here, what was the region before this line passing through? The region was the whole thing, right? But now that the line passes through, it makes 2 regions out of that. How about in here? There was a region, the line passes through, splits it in 2. So can I write this in a mathematical form? So the new regions, n plus 1 line, creates how many new regions? How many? So I've got a bunch of regions from before. That was the non-dotted lines. Now I cross the dotted line. How many regions are there? Extra. A bunch of the existing regions have been split in half. The question is how many? Exact. If I have n intersection point, how many regions were split in half? This must be n plus 1 because there were n, on the line. If I have 3 points, then there's like 4 segments of the line, right? This will be this segment here, this segment here, this segment here, this segment here, and this segment here. Each one of the segments of the new line splits some region in 2, right? So this is n plus 1 region. So now if I add up n squared plus n plus 1 divided by 2 plus n plus 1, would I get that one that's in here? That's n squared plus n plus 1 plus 2 times n plus 1 divide by 2, right? Because I moved this up. With this is this equal to that one? I don't know. N squared plus 2n plus 1 plus what do I need? Plus 1 plus 2. You can check this out. I think I did it with 2 here. Yeah, it's a 2. So I now have a 2 here. So it's 1 plus the 1 plus 2 is the 4. Okay? So how do I think about this problem? I was like, I have these lines. It's a structural problem. I think of the n lines, and then I think of the n plus 1 line cutting through some of the regions. I have to count how many regions got split in half if I add those regions. Let me give you an exercise for next time. I want to do the following problem next time. I want to say, remember the binary search tree? I'm not going to do the problem now, just give it to you. If I have n items or n values, and I make a binary search tree out of them, I want to prove the height of the binary search tree is at least log base 2 of n. And the way I want to think about this is if I have a binary search tree with a root, there is some subtree here and some subtree here. How do I use induction to prove this problem?
This is where we say our goodbyes. Literally dying. And take it home to the family. Introduce him to the family.
How did Joe form here? I do know her like that. She introduced herself to Joe. Yeah, are you sure? Pretty sure.
I know maybe but that's a formal to be sure. Because that's the smallest.
Yeah, because it's the smallest.
But then all of your present,